Okay, we'll get started. So thank you all for coming. Welcome to the AI in Science seminar series. This is a collaboration between Penn AI, the Innovation in Data Engineering and Science Initiative here in the School of Engineering, and DDDI, the Data Driven Discovery Initiative in the School of Arts and Sciences. This series highlights interdisciplinary research at the intersection of artificial intelligence and the sciences, and aims to spark new collaborations between science and engineering at Penn and beyond. Today, we're delighted to host Professor Bhuvnesh Jain. Bhuv is the Walter H. and Lenore C. Annenberg Professor in the Natural Sciences in Penn Arts and Sciences, Department of Physics and Astronomy. Bhuv also serves as co-chair of the Penn AI Council, together with Renee Vidal, helping to shape Penn's university-wide strategy and investments in AI research and education. But most importantly, Bhuv is also the co-director of the Data Driven Discovery Initiative in the School of Arts and Sciences, which is I have the pleasure of managing as executive director. Bhuv's research focuses on cosmology and gravitational lensing, exploring how the large-scale structure of the universe and the acceleration of its expansion can be understood through the interplay of theory, data, and observation. His work has made foundational contributions to our understanding of dark energy and the use of fluke lensing as a probe of cosmological physics. More recently, Bhuv and his collaborators have been applying data-driven and machine learning approaches to cosmology to address the challenges of analyzing the massive data sets generated by modern sky surveys, such as those from the Vera Rubin Observatory's Large Synoptic Survey Telescope, which came online this summer. His leadership in bridging data science, AI, and the physical sciences exemplifies exactly the kind of interdisciplinary work that the AI for Science series seeks to highlight. So I'm very excited to hear what he has to share with us today. And without further ado, please join me in welcoming Professor Bhuvnesh Jain.
Hi, everyone. Thanks a lot for joining this talk. I'm thrilled to have most of my collaborators in this room, and I will introduce them as their work shows up. But I especially want to thank Sunao Sugiyama, without whom this talk would have been canceled. I started preparing this talk after dinner last night, and my laptop died in the process of an operating system upgrade. And so now kindly loaned me his laptop. So I was waiting for him to come in this morning, which is when I started preparing. So apologies for some possibly, I don't know what's the right word, chaotic sequence of presentation. That's my outline. I'll describe a little bit of astrophysics, how we map the mass distribution of the universe, what are the cosmic puzzles, and then I'll talk about two machine learning topics, generating large-scale structure in the universe, and how to test observations with big cosmic surveys, test cosmological models with observations. So I have just one or two slides on some introductory material. This is the cartoon of the expanding universe. There was a big bang 14 billion years ago. There was things before the Big Bang, but that's the realm of speculation. But we do think that from about when the universe was the size of a tennis ball, our entire observable universe, we have a theoretical description. So, the first nuclei formed in the first few minutes. And then when the universe was 380,000 years old, the hot plasma had cooled enough that you could form neutral hydrogen atoms, and light streamed freely through the universe. When it was around 1 billion years old, a lot of the galaxies had formed, and we are sitting here looking back at this universe. So if you go to a big telescope and you take a minute-long exposure, then you're seeing galaxies from when it was 1 billion years old. So we can see across 90% of the observable universe quite easily. Um, and so the game in cosmology is to map enough of the universe to get a fair sample of it to test theories. And with telescopes that are currently under commissioning, so they'll start there's a big telescope that'll start observations in December, another that'll be launched in space next year. We are literally mapping 90% of the entire universe. Like you can get to 90% of it in one line of sight, but to cover the whole sky, that's still a challenge. I use a particular method of learning about the universe called gravitational lensing. And so this is a way of learning about dark matter and dark energy that I forgot to introduce. So the expanding universe is dominated by something called dark matter, which is present in every galaxy. It's going through our solar system. Quite likely there are particles of dark matter going through your body as we speak, but it doesn't interact except through gravity. So it's very hard to spot. And then dark energy fills all of space. And these two make up more than 95% of the energy of the universe. So the standard model of cosmology is both simple and mysterious. It says the inevitable quantum fluctuations in the very early universe produced irregularities which grew via gravity as the universe expanded. And the expansion was driven by dark energy and dark matter. So a point that I'll return to is that for 100 years, there's been the theoretical possibility that pure vacuum has energy. And that energy has been the simplest candidate for the dark energy. It's specified by just one number, its energy density. So that's part of the standard model of cosmology. Any questions so far? I know this is like a half-hour introduction I've compressed in 2 minutes. Okay, on to lensing. So within this universe, here's a Hubble Space Telescope observing a galaxy a few billion light years away. The light from this galaxy doesn't travel in straight lines, it travels in curved paths. And if there's a really giant galaxy cluster, you'll get multiple images of this galaxy. And I know many of you are familiar with this effect, so I thought I would show you one particularly crazy illustration of it, where in this special patch, a supernova going off in this galaxy got imaged 4 times as the light went around this little galaxy. So this galaxy has stars, but also a bunch of dark matter, which bend these light rays. And so with the supernova that was detected, there was a prediction and looking back in time, that because light was coming on different paths, it takes different travel times. And so it was predicted it would be seen in this image sometime later, and it showed up. So the mathematics of curved space-time that Einstein taught us really seems to be how the universe works. So that was a very dramatic instance of gravitational lensing. I'm more interested in the lensing of a typical galaxy. So this is a cartoon of a few typical galaxies, and they are lensed a little bit. So these are our wallpaper, and we look at how it's distorted, and we use that distortion to map the distribution of matter in the universe. Okay, so if you were looking at me and there was a black hole or some dark matter in the way, my face would be stretched in different ways. And if you knew what a human face looked like, you could infer the stuff that's bending light. So statistical version of that is how we map the mass distribution of the universe, but the typical lensing is really weak. There were some very famous theorists who in the 90s said, it's cute to calculate, we'll never observe it. 3 years later, we made the first detection, and then it took another. In fact, Einstein himself said lensings, when he calculated the Einstein ring, he said, cute, never going to find it, because that required a coincidence of a source, a lens, and the observer on a straight line. So that was detected in the late 70s, and then the weak version was detected in the year 2000. And then in the last decade, with a survey called the Dark Energy Survey, we've started to make maps of the dark matter. So this is 10 million light years. This is one of the biggest superclusters measured. The blue is voids. So this is one of the largest voids ever detected. And then, of course, you can make the dark matter map and then look at the light itself. And so in the center of this cluster, you see a concentration of elliptical galaxies. And this void is an unusually dark part of the universe. So we see stuff in light, but it's the dark matter that is the full story that cosmologists want to know. And you can see the resolution of the dark matter map is very coarse because the lensing effect is so weak. Any questions so far?
So did they think it wasn't possible because of instrumentation?
Yes.
Aside from the being in the right line.
Mainly because of the atmosphere. The atmosphere blurs light. And so, galaxies aren't round to begin with, and then they're distorted by 1/10%. So, and these are faint galaxies, so you have like 30 pixels. So you have like this really grainy image that has a tiny distortion. So we needed like 1/3 of a million galaxies to detect the coherent distortion. That was the first detection. And I'll show you the maps we are making now with 100 million galaxies. So it's really a sample size game.
It was
along with exquisite understanding of the instrument.
It was 1/3 of a million in one field of view.
Sorry?
In one field of view, 1/3 of a million? Like the wallpaper is 1/3 of a million galaxies, is what you're saying.
Yes. So lensing is our method. What is our motivation? The motivation is to learn about what's dark matter, what's dark energy, what's this standard model. And in the last years, there have been some wrinkles. So there's there's two cosmic puzzles. One is that the universe is expanding faster than predicted by that standard model. There's the structure formation puzzle, that the growth of structure is a little bit slower than predicted. Both of these are hotly debated in the observational community, but they definitely motivate a lot of theory and observation. So my work relates more to the structure mismatch. And so this is the visual version of it. This is the large-scale structure of the universe, where each yellow dot is a big galaxy. That's predicted by theory. The fainter version is what we learn from data. So the particular pattern is different. That's fine because it's a stochastic field. But the fact that this is less prominent, the fluctuations are weaker, is a possible failure of the theory. In the last year or so, there's an even more dramatic puzzle, which is that there's been a very compelling claim that dark energy is evolving over cosmic time. So the density of dark energy has been increasing over much of cosmic time. And this is a very complicated story from the data analysis point of view, because you need to combine different ways of measuring cosmology. But if you buy it, and most of us certainly take it very seriously, it's a very big deal. Because once you step away from pure vacuum energy, you're talking about new particles, new interactions. Dark energy cannot evolve unless there's what we call new fundamental physics. So if this holds up, it's one of the biggest, if not the biggest, certainly the biggest discovery in astrophysics of this century. So since I'm talking about it, you don't need to worry about how these contours were obtained. I'll show you why we take it seriously. This is a particular combination of data, but this is the standard model. So this is, if you like, the derivative of the energy density, zero derivative. And this is the particular ratio of pressure to density that corresponds to vacuum energy. So all previous data had contours that look like this, consistent with vacuum energy. Now the contours got tighter and they shifted a little. And in these three data combinations, they are 2 to 3 sigma away. So at 99% confidence level, there seems to be a detection. Still hotly debated, but could be settled within the next 2 years. So I'm going to go back to lensing and tell you how we do cosmology with lensing. So I showed you a smaller map. This is the biggest map that we have with galaxy surveys of the dark matter distribution. The shape on the sky is related to practicalities of the telescope being in Chile and so on and so forth. But you can see there's a kind of repeating stochastic pattern, cosmic void, superclusters. The scale now is 100 million light years. And this map took the shapes of 100 million galaxies to make.
Can I ask a question? So when you say that's 100 million light years, this is part of the sky we're looking at, right?
Yeah, so if like you were observing my face and you were the observer, then the mass distribution between us, that scale is 100 million light years.
So then how far away from us is that mass distribution, right? Because doesn't that set the horizontal?
Yes. So like I am a few billion light years from you, and the mass distribution, it's a projected field, so it's not a precise number, order a billion light years. Other questions?
Yeah. How did you identify that many lenses?
We don't identify them individually. This is, so we have this wallpaper of galaxies, and as you know, it's like an inversion problem. So we just, we have all this wallpaper, and then we have imagine a pixelized 3D pixelized map of space in which we infer the mass density in each pixel. So now that we have this map, sorry, I've changed the color scheme because in each paper, people choose their own color scheme. Fiercely independent students and postdocs. So given this map, how do we compare it to theoretical predictions? I'm going to show you a simulated map. Again, the particular, the fact that there's a hotspot here, and there isn't one here doesn't matter. It's the nature of the pattern. That's, reasonably similar. This one is definitely wrong. This one's also a decent match. So how do we actually compare theory and observations? Before we do that, I'll talk about one challenge. We need to generate these maps. So, for simplicity, let me say that you have 5 competing theories. Each theory is specified by a set of parameters. How much dark matter, how much dark energy, what's the, initial conditions. And so for each choice of parameter, suppose you have like a few parameters, you need to simulate maps of every choice of parameters and then compare them to data. First, you decide, is it a good fit for any choice of parameters? And then if it is a good fit, what is that value of parameters? So I said that pretty fast, but the bottom line is that we need thousands of simulations. And a simulation takes a few days on a supercomputer. So it's a major computational challenge, and it actually is limiting the space of theories we can test. So I'll describe an approach that Kunha, where are you, developed to generate maps really fast. So in cosmology, I remember I mentioned quantum fluctuations. So we think it all began as a Gaussian random field, and he figured out this mapping that exponentiates the field and generates what's called a log-normal field, which looks reasonably like the structure in the universe. This was well known. So let me just skip
Wait,
that.
sorry, if we go back to the core computational problem of the full simulations, just so I understand, what's the sort of main computational complexity in doing the full version before you?
Oh, right. So like gravity is a long range force. So the way we do it is really brute force. You start with 1 trillion particles. Each particle has the mass of 1/100th of a galaxy. And you set them off when the universe was 100 million years old. And you just then take 10,000 time steps with each particle interacting with every other particle.
Oh, and you need them all to interact even with very distant particles?
There's, tree methods we use to go from n squared to an n log n computation. So there's a lot of tricks, adaptive meshes, tree structures, and so on. The bottom line being it takes a few days. Thanks. Yeah, this is relevant. So Kunha used his own guesswork and then used symbolic regression, which is a way of figuring out, you take a family of simple functions and you figure out which ones describe your curve. And he came up with this 5-parameter function that described the mapping much better than people had done previously. So again, I know I'm going fast, but this is the probability distribution function of the density. And the solid is what's measured in simulation, so that's a ground truth. And the pink one is like his penultimate best fit, which you can see is vastly better than what people in the field use. Of course, we are aiming high, which is to say we are going pretty far out in the tails. Often people were just happy enough to fit out to the 2 sigma excursion, but we wanted to get out to 4 sigma. Okay, so this is the distribution function of the density that he was able to fit with this Gaussianizing trick.
So just to be clear, like obviously these are not like analytic derivations based on some fundamental theoretical principles, right? These are just curve fitting exercises. Is there more than just a sort of blind curve fitting link? Like, is there some kind of relationship between the functions that you've discovered and maybe more basic physics principles?
Yes and no. Let me address this in 2 more slides or 3 more slides. So what he can do now is to generate maps that look like this. And if you really came up here and looked at my laptop, you could see subtle differences. But it turns out the best telescopes in the world, even 3 years out, will not be able to distinguish his map from the true high fidelity map. So they're almost good enough for many purposes. So we have these analytic simulations, and when you do inference, they're really powerful. Because when we run a data analysis chain, we actually have to run it 1,000 times, because we need to vary what the optics might be doing, and this uncertainty and that uncertainty and this null test. So having analytic maps that are almost good enough is pretty powerful. And to address your question, something I glossed over is that the maps have to be right at every resolution scale. When I showed a histogram of a PDF, that's at 1 resolution scale. So how to check that something that you got right on 1 resolution is correct on all resolutions? That's real work, and that's where you use some of the physics. But at the end of the day, once you have this fitting function, it has 5 parameters, and there's some initial conditions. They have 5 other numbers. So you basically boil down that whole map of 1,000,000 pixels to about 10 numbers. And then you can ask, what physics do these 10 numbers correspond to? And so he can transform his 10 numbers to the evolution of dark energy, for example. And so there's a lot of insights to be gained there. But it's mainly like for a practical purpose. Other questions?
Yeah, what are when you say all statistical tests, I mean, that distribution presumably is gonna be somewhat smooth, right? So that curve to me seems like with 10 numbers, of course, you're gonna hit that kind of curve. And do the other ones at the other resolutions look very similar? I guess I'm wondering what tests you'd expect to not be right, given this.
When I say all statistical functions, I'll describe 1 or 2 next. But like correlation functions, power spectra, topological measures of the maps. So the main caveat is that his maps work up to some smoothing scale. We can simulate finer scales where his mapping fails, but the data has its own required smoothing. And so for the data that we have and the kind we expect to get in the next few years, it's good enough.
Have you tried using machine learning method to distinguish them?
To distinguish the maps? Not quite yet. Yeah, good question. I want to talk about a different method of generating maps, which some of you are maybe more familiar with, diffusion models. So as you know, when you generate pictures of cats and dogs, it works something like this. A diffusion model learns things about this image by adding progressive steps of noise until it has pure noise. And then there's a magic trick that lets you go from the pure noise back not just to that dog, but to other families of dogs. I won't say more about diffusion models, but that is no longer the uniquely best, but state-of-the-art model for generating images. So I'll show you now something that Michael did in the summer of his sophomore year. Try not to think back about what you did in the summer of sophomore year, otherwise, you will feel embarrassed. But Michael wrote this amazing paper with a postdoc, Supranta Barua, on using diffusion models for cosmology. So let's just focus on the middle panel. This is the ground truth. And this is the way the diffusion model works. You try to recreate that ground truth given noisy observations. And it takes a bunch of steps, and it gets better and better until you have something that's not identical, but pretty close. So this is the dark matter at some distance or time from us. This is further away, that's closer, but they all show the same thing. So they took a bunch of simulations and learned how to generate these maps. And not only did they learn how to generate the maps, they also learned how to reconstruct the underlying field from noisy data. So diffusion models are magic to begin with, and then they did a second step of magic, where once they learned how to generate the mass maps, they had an analytical model of the observational noise. And so without further tweaking, no conditioning, they could take the noisy maps and reconstruct the true field. And so they could generate samples. You know, this is the nice thing about diffusion models. You can generate multiple samples, which let you estimate the uncertainty. You can average them, and you can compare them to the truth. So you can see each sample has some variation from the truth. When you average them, you lose a little resolution, but at this point, you have very high confidence in everything you've generated. And to show you how much better they are than what previously existed, this is the method that has been used in cosmology for 30 years. So their gain in resolution is a factor of 5. It comes at a price that I'll describe in a minute, but it's far better than this method. But you can see you'd have to smooth this further to get reliable structures. But this method assumes nothing, just gravity. Whereas the diffusion model is trained on simulations, which says that it's not just gravity, but it's the fact that in an expanding universe, gravity generates structures that look kind of like this. And so it's learned the particular workings of gravity in cosmology through a set of simulations. So its maps are great as long as you're not out of distribution. Whereas these maps, the only thing out of distribution is if you break Einstein's gravity. Does that make sense? So even so, I was astonished at this factor. And so that's really great to study many things that astrophysicists really care about. In particular, what's the distribution of dark matter relative to stars and relative to hot gas? And that comparison, which is like an entire field of astrophysics, was totally limited by the resolution of the dark matter maps. Because observing galaxies is really easy at very high resolution. And so gaining this factor of 5, we're in the process of applying it to the dark energy survey. I'm really excited at what we're going to find with this new resolution. All right, so I'm done with the main part of my talk. And let me just summarize it. The simulations we just discussed, Kuhnhau's model in which he can generate 1 million maps on his laptop is super useful. Diffusion models are of course not as cheap as Kuhnhau's analytical model, but they're at least 100 times cheaper computationally than the true simulations. And we have solved the reconstruction problem with them. And we are now figuring out how to apply it to data. Anything you'd like to add, Michael?
Pretty happy with that song.
So going back to sort of the comparison of the diffusion model and the older models, you mentioned something which I thought was interesting, where you said it sort of constrains the gravity equations in a more realistic way, I guess.
Yeah.
Or that's how I'm interpreting it. Can you translate that down to some kind of analytical framework that ideally constrains things more than, say, like Einstein's equations? Like, can you say, well, this space of the equation is not observed under this set of conditions for a certain physical reason? Or, and what sort of would that look like?
The funny thing is that like 1/r² gravity is still really hard to analyze. So when a bunch of particles are interacting via 1/r² gravity, will they collapse into a collection of black holes? will they form one-dimensional filaments in 3D space? Will they, now I'll tell you what we think actually happens, that they first collapse into sheet-like structures, then matter flows along the sheet-like structures into 1D filaments, and at the ends of the filaments, the crossings of the filaments, we form galaxy clusters and galaxies within them. So this is the hierarchical formation of structure that back in the 80s, people had guessed at using approximations. But really to see it, we waited for good simulations. And there's still this question, this chicken and egg question, do the smallest galaxies form first or the superstructures form first? And it's a little bit of both. And I'll show you pictures of how this kind of hierarchical structure is quite common in nature.
Thanks.
But there's no like super clean insights that come from theory. All right, how much time do I have, Colin?
We go to 1, so we got 20 minutes.
Okay, great. So I'll go for 12, 13 minutes. All right. So how do we test theoretical models? I'll describe very briefly 3 steps. One is how do you go from 1 million pixels to 10 numbers, extracted from a map. So Kuhnhaus approach gives you a hint, but there's other more systematic approaches to do it. And how do you get posteriors on your theory from this summary statistic? And then this is one approach. And then there's the deep learning approach where you say, here's a cat. Is it an orange tabby or a calico? So you say, here's my observed universe. Is it one in which dark energy is evolving or constant, and so on. So this is the map I just mentioned. This is cosmology. And this is the surface of the sun. This is ocean turbulence. This is an Ising model, microscopic, and this is a mathematical model. So let's look at these 4, which are natural phenomena. You can certainly see where the color scheme is similar, that you have this hierarchical structure, whether it's the sun or the ocean or the universe. So this is, fluid mechanics, magnetohydrodynamics. This is just gravity. But you see that you need to measure fluctuations on multiple scales. A little reminiscent of how the attention mechanism captures relationships between words on all scales in one shot. So the lower panel is an analytical model based on wavelets, where they used a basis expansion, so used 100 numbers to generate new maps. So it's a much more detailed attempt than Kuhnhaus fitting function, and it's motivated a little bit by CNNs. They take like thresholding and absolute values. And you can see it does a pretty good job, but far from perfect. But if you try to do it using traditional methods like Fourier expansions and stuff, it would be awful. You would train like 1,000 coefficients for one of them, and then on the others, it would just like this would be awesome. So there is some progress. And so wavelets look like this, compensated Gaussian filter functions, and they have some very nice properties. They're compact in real space and Fourier space. And you can take this large scale structure like map, you can separate scales. That's really important. Like if a black hole is redistributing matter, it'll do it on these scales, supermassive black holes. If the initial conditions are slightly different, they'll do it on these larger scales. So separating scales is really important for both theory and understanding noise. And these wavelets let you do that. So I'm now jumping to like a final result. using what's called simulation-based inference. In physics, it's also called likelihood-free inference. I don't know what's more common, where the idea is that you generate a bunch of simulations and you compare them to observations via these summary statistics. And this involves dimensionality reduction, building emulators, neural posterior estimation, and so on. Using these wavelets and SBI, we get constraints that are twice as tight. So these are 1 and 2 sigma contours, and the solid lines are sort of the 2-point function traditional way to do them. And so these are parameters of the stock energy model: energy density and fluctuation amplitude. And okay, this is energy density, this is fluctuation amplitude. So these are related to the puzzles I mentioned earlier. So you can see we can do twice as well by using this analytical attempt to capture more information. It turns out that so far, this is about as well as anybody's done. The attempt to learn everything from the map, one of the ways to do it is via deep learning. And so I think most of you know how a convolutional neural net works. You take an input image and you convolve it with a filter, and you learn that filter, a set of filters. You pool it, convolve it, pool it, and then pass it through a dense neural network. And then you can train it for any desired goal. Is it a cat or not? Is it orange tabby or a calico? And so on. So this same approach can be applied to our dark matter maps. So this is maybe the first paper that tried to do it 6 years ago. And they showed that it performs pretty well. They used industry standard, ResNet and stuff. And then Kunhao said, well, I want to build my own CNN. And I don't see why I need like 100 layers and all this, the millions of parameters that ResNet has. And so he built a much smaller CNN, and he figured out some ways to actually make it better than the industry standard. So this is one result that shows what the industry standard loss function during training and test was. So there was a clear evidence of overfitting. He got a better loss function with no worry about overfitting. At the end of the day, his contours were also a little tighter, but it was the simplicity and these properties of his CNN that were more important. And so there was some data augmentation, there was some choice, which to me was completely mysterious, of average pooling and max pooling, and some regularization by shuffling the final layer through which he got this result. Anything you'd like to add, Kunhao? We've also played with transformers, vision transformers. And so there's a particular variant of them that seems to perform very similarly to CNNs. And we haven't pushed very hard to see, as you increase the training data, whether transformers start to perform better or not. Just some musings about where machine learning is headed in cosmology, and I'm happy to discuss other branches of at least the physical sciences. It's all over the analysis pipeline. You use neural nets for data compression, emulation, and so on. Whether we can do end-to-end testing of theories with deep learning is pretty hotly debated. I would say at least half of my colleagues won't believe a result that comes from CNNs or transformers. They'll say, I just want to repeat it all using my physicist approach. And you tell them that, but your approach is weaker. If you find something, you won't be able to replicate it. And they'll say, well, I'll wait till there's more data. So this is the state of play. There are the people who are more versus less open-minded. My own view is that we have already had to embrace simulations. So when you're doing theory via simulations, then you can always design tests for whatever method you use. So I'm pretty open to this. That said, like I told you, our wavelet type summary statistics and Raphael and so now have developed another one called 3-point correlation functions, which is probably far from most of your experience, so I didn't talk about it. They do comparable to the CNNs right now. Whether we can scale the training data and improve performance, whether we can build foundation models, these are early stage questions, as is interpretability. If we can make some serious progress with interpretability, that would help convince the community. And I have a collaboration with some folks in Whistleblower using the sum of parts method on interpretability. So they take our CNN and they wrap it in their thing and tell us which parts of the image are driving the finding. So we are still exploring that. I'll wrap up by saying that Cosmology had built the standard model with 2 mysterious ingredients, but now there's questions around even that standard model, the expansion rate, the structure formation, and evolving dark energy puzzles. And this certainly, but each of these could well be pointing to new physics. So many of us have the feeling that it's this moment of argument and confusion that may be pointing to a huge discovery. So while we argue and debate, we are also gathering new data, which is probably what we need to settle things. And underpinning all that, along with gathering new data, the developments in methodology are a place where people are working very intensely. Thank you. Other questions?
Thank you for the talk. Talked about using AI to analyze the data. Have we ever tried using AI for data gathering?
People use AI to for the functioning of the telescope and for the design of the scan pattern. So there's one thing that you can observe. Stars are like point sources of light. So if you observe a star, you can learn what the atmosphere is doing real time.
In real time.
In real time. And then what people do is there's like the mirrors of modern telescopes are the size of this room. They're like huge and heavy as hell. But they're actuators at the back of the mirror. So there's 20 actuators. And you can adjust the principal modes of the mirror to compensate for what the atmosphere is doing. And so that feedback loop is called active or adaptive optics. And so that's one place where machine learning is used. Another is that if you want to address this particular question, should you, simplest question, should you go wide or should you go deep? In other words, given a year of observations, should you look further to catch the most faint galaxies or get more sky? So there's very finer variations of this question for which people use machine learning because the actual scanning is very complicated. The Earth is rotating. seasons are changing and which part of the sky you can access where is complicated.
It's a very big general question, but so I do experiments that are much smaller scale and with way fewer incredibly complicated parts in the chain. And it just like strikes me when I'm kind of teaching someone to do experiment, I try to have them remove as many opaque steps as possible. So they actually know what's going on in the pipeline. And it just, I wonder like how does the field feel about adding more steps into this chain, like with AI, for instance? Or are they just kind of immune to that because you have to be okay with someone else's hardware that you don't understand in this chain? Like, do you think that cosmology maybe is a place where it'd be easier to use this stuff because people would be more accepting of that? Or am I just way off?
I mean, let me just say one thing, that compared to the best analytical approaches, where you decompose the field into different scales, fit these complicated functions, this is considered elegant, because it's analytical.
Sure.
But the deep learning approach is simpler. You're just comparing map to map. And there's a lot of, ad hoc decisions about hyperparameter tuning and regularization that you make in between. But you're not going from a map to some coefficients and dimensionality reduction of the coefficients and emulation. So the traditional method is itself very complicated and pretty much simulation based. The starting point is simulations. So, yeah.
So you think that makes people more willing to adapt things like this then? Adopt?
It certainly makes the deep learning approach appealing. Yes. But the black box is a major issue. Is this observed universe out of distribution? That's the thing that keeps people awake at night.
Right, in a way that you would have no way to know to measure even, right?
There are many indirect ways to measure it, yeah. But it's complicated. That's why I'm stopping there.
Well, actually, I had a question exactly about the out of distribution settings, right? With LLM, we've also struggled occasionally with out of distribution or out of domain problems, right? A big research agenda is to come up with those problems, to probe those models, test their capabilities, and to improve them, right? And what does a out of distribution test set in cosmology look like?
You go to your theorist friend and you say, what's a really ugly, crazy model? Give me 5 of those. And you simulate those. So, in other words, it is limited or generated by the imagination of theorists. And then you say that, okay, I'm going to break Einstein's gravity in one case. I'm going to have a crazy form of dark energy in another case. I'm going to make dark energy and dark matter interact as a third case. So you try to span the range of, I'll collapse a 7-dimensional universe to a 3-dimensional one. Those are your out of distribution test cases.
I was thinking maybe along a slightly different line where maybe you train your model or you fit your model on, a subset of the scales, right?
Mm-hmm.
And then you're like, okay, well, we've, left out this nth scale and let's see whether it can actually generate the distributional properties observed at that scale. Is that something that's done?
Great point. Yeah, we do. There's like a standard set of tests we do. And for example, one is early cosmic times versus late cosmic times. So when they discover this evolving dark energy, people scrutinized which cosmic epoch is it coming from? And what if we leave this one out? What if we leave, yeah. Yep.
Yeah, just 2 general questions. One, would you be able to share this presentation with the people here today?
Sure.
Second, which data sets would you recommend for researchers who are just getting started, like official data sets or benchmark data sets? Which would you recommend?
If you want to touch real data, then you can Google dark energy survey as one example, and you can just download these dark matter map to play with. If there are also like challenges, there's a very recent challenge where you're given a bunch of simulated maps and you're asked to infer the cosmological parameters. And the goal is to produce the most constraining, least biased inference. And I can tell you about that. I think that's on Kaggle.
Okay, let's thank Bhuv one more time. We have one.
And then
Yes.